research regarding the examination of the methodologies and mechanisms that underlie fatigue thresholds. Just a general outline of this presentation today and what we're going to discuss is first we'll look at what are fatigue thresholds, some definitions, some examples related to both metabolic and neuromuscular fatigue thresholds. And then we will look at the application of fatigue thresholds. There's a variety of applications involving performance, examinations, fitness assessments, and also some clinical potential applications to these models. And then we'll move into the origins of critical power and that concept, which was kind of the focus of my doctoral work, and specifically looking at a new protocol for determining critical power from a single work bout. And then we will look at how these fatigue thresholds relate to the exercise intensity domains and the responses that we see, the physiological responses that we see when exercise is performed at critical power, and the potential mechanisms that may underlie fatigue and during endurance and sustained exercise activities. And then we'll move into the critical heart rate concept, which is the application of a physiological parameter to these mathematical models. And finally, looking at future studies and where all of this research has led us to the future. So to begin, fatigue thresholds, just a general definition, they're submaximal exercise intensities that demarcate the exercise intensity domains. So exercise performed above a fatigue threshold results in certain physiological responses, and exercise performed below that threshold results in different physiological responses. And they're determined from a variety of parameters: physiological, mechanical, looking at neuromuscular and metabolic parameters. For example, we have the gas exchange threshold, which is determined during an incremental test. And this is the point of nonlinear increase in the volume of carbon dioxide produced relative to the volume of oxygen consumed. A separate fatigue threshold that can be determined during the same incremental test is the RCP, or the respiratory compensation point. And this is the point of nonlinear increase in ventilation or hyperventilation relative to carbon dioxide. And this occurs at a higher intensity than the gas exchange threshold and represents different physiological responses. And a unique fatigue threshold that is the focus of a lot of work from my previous lab at Nebraska is the physical working capacity at fatigue threshold. And this is determined from a series of submaximal work bouts and the amplitude of the EMG signal, which is recorded during each of the work bouts and plotted over time. So these are 2-minute work bouts recording EMG amplitude, which reflects muscle activation. And the PWC-FT is defined as the highest power output that results in no change in muscle activation over time, and the lowest power output that results in a significant increase in muscle activation over time. So for this example, this is 230 watts where we see the first increase, and 200 watts, which was the highest power output where there was no change. So the average of 230 and 200 is 215, and the estimate of the PWC-FT is 215 watts. So theoretically, if we had a subject perform exercise at 215 watts, we should see no change in muscle activation over time. There are a number of applications to these fatigue thresholds. And one interesting application is often looking at the prediction of endurance performance. The critical power concept can be used to predict time to exhaustion, but it can also be an excellent predictor of marathon performance time, as well as the lactate threshold, often a better predictor than VO2 peak. Fatigue thresholds are also used to describe and examine the effectiveness of exercise training programs. For example, critical power has been used to determine the effectiveness of a 6-week training protocol where subjects performed exercise for 40 minutes cycling at the maximal power output that they could to sustain for 40 minutes. And then they underwent a 6-week training protocol and then retested that. And they showed a significant increase in the power output they were able to sustain for 40 minutes, which was reflected by a 30% increase in their critical power. So it is sensitive to training adaptations. We also use fatigue thresholds to examine mechanisms of fatigue. And one way that we've done that in the past is through some supplementation. We supplemented subjects with sodium bicarbonate, which theoretically should reduce the effects of the hydrogen and iron concentration for buffer and maintain pH within the muscle. And we looked at the effects of this bicarbonate supplement on the PWCFT and neuromuscular fatigue. And acute supplementation had no effect on estimates of the PWCFT. So this suggests that hydrogen ion concentration and decreases in pH may not be the most important factor in driving neuromuscular fatigue. We also have used fatigue thresholds to examine the efficacy of nutritional supplements. For example, we looked at the effects of arginine supplementation over 4 weeks on estimates of the PWCFT and neuromuscular fatigue. And we saw a 12% increase in the neuromuscular fatigue threshold, which suggests that potentially, because arginine is a precursor to nitric oxide, which is a vasodilator, that neuromuscular responses may be more sensitive to blood flow and the availability of blood to the working tissue. We have also used these fatigue thresholds to determine exercise capacity in athletes. And oftentimes we look at VO2 peak, but we also look at the lactate threshold or critical power to determine their performance capabilities. And we can also use the anaerobic work capacity that we get from the critical power model to determine their capacity to perform anaerobic high-intensity exercise. And some relatively newer applications are with the clinical population. Some of these fatigue thresholds are determined from submaximal exercise intensities, like the GET can be performed from a submaximal protocol. So that may have applications with patients who have diminished exercise capacities, specifically looking at obese populations or the elderly could potentially be used as a way to prescribe and examine the effectiveness of exercise training protocols. One of the fatigue thresholds that has been one of my focal points in research is the critical power concept. This concept was originally developed by Mono and Shear in 1965 for intermittent isometric muscle actions for small muscle groups. And then it was later applied in 1981 by Morikani and colleagues to whole body exercise and dynamic exercise during cyclodrometry. The salient feature of the critical power test is that it requires only a cyclodometer and a stopwatch without the need for expensive metabolic equipment or electromyography measurements. For this test, subjects perform a series of submaximal work bouts to exhaustion, and the time to exhaustion is recorded. And then the product of power output and time to exhaustion, which is the work, total work performed, is plotted against time to exhaustion. So we get a highly linear relationship where the slope of this line theoretically represents critical power, or the highest power output that we can maintain for an extended period of time. And the y-intercept represents the anaerobic work capacity, or the total amount of work that can be performed using only stored energy sources, ATP and phosphocreatine. So from this test, we get estimates of both aerobic and anaerobic capabilities. And then a third parameter can also be estimated from this concept, and that is the time to exhaustion at any power output greater than critical power. By plotting each power output against time to exhaustion, we get a negative curvilinear relationship that has an asymptote that theoretically represents critical power. This hyperbolic relationship between power and time is termed the power duration curve. And we can predict the time to exhaustion at any power output greater than critical power by rearranging this linear equation from the work limit time to exhaustion relationship. The key concept of this figure is that the power outputs that we use to determine this work limit T-limit relationship, when plotted, define the slope of this hyperbolic curve, or the asymptote. So the slope of this line defines the asymptote of this curve, which then theoretically is critical power, or the highest power output that can be maintained for infinite time. Because the critical power test requires a number of exhaustive work bouts and can be strenuous for participants, researchers have continuously tried to develop new protocols to improve the practicality of the critical power test. And recently, researchers Burnley and Bonatello developed a 3-minute all-out test. For this test, subjects perform all-out exercise for 3 minutes on an electronically braked cyclogometer, theoretically exhausting anaerobic energy source and resulting in a power output at the end over 30 seconds that is reflective of exercise performed relying solely on aerobic energy sources, theoretically representing critical power. And then the integral of the power-time relationship above critical power is the anaerobic work capacity. For this test, however, subjects must first initially perform an incremental test to exhaustion to determine VO2 peak and the gas exchange threshold, which is then used to calculate this value 50% delta, which is just half of the distance between VO2 peak and the gas exchange threshold. So the linear factor is then used to set the resistance for this 3-minute all-out test. So in actuality, this protocol requires 2 maximal tests and the use of expensive metabolic equipment and an electronically braked cyclogometer. So during my graduate work at the University of Nebraska, we conducted a number of studies to look at the methodologies and mechanisms that underlie these fatigue thresholds and improve the practicality of some of the protocols. I don't have time today to talk about all of these studies, but I would be happy to talk with you at any time that you have available and would like to discuss any of these that we don't cover. But one of the first studies that we conducted was an examination of the 3-minute all-out test and an attempt to improve the practicality of this test. Because a lot of people don't have access to metabolic equipment or electronically braked ergometers, we designed a protocol based solely on body weight, using a mechanically braked ergometer like a Monarch that is more widely available in laboratories. And so we did some pilot work, and we found that when we based the percentage, approximately 3.5% and 4.5% of body weight, we got estimates of critical power and anaerobic work capacity similar to those from the multiple work bout model, the original model, and the 3-minute all-out test of Burnley and Bonatello. So this protocol was analogous to the Wingate test, but performed over 3 minutes, and resistance set just based on body weight. So we conducted conducted a study, and we had subjects perform 4 separate estimates of critical power. They did the original model, the 3-minute all-out test of Burnley and Monticello, and then 2 different protocols of body weight percentage. And we found that critical power at 4.5% of body weight resulted in estimates of both critical power and anaerobic work capacity that weren't different from either the original model or the 3-minute all-out test. So we had developed a protocol that was actually a single test where we could determine both aerobic and anaerobic capabilities without the need for expensive equipment. One of the primary applications of fatigue thresholds in research is the examination of the exercise intensity domains. And Gacy and Poole described 3 distinct exercise intensity domains: the moderate, heavy, and severe. And the moderate intensity domain is defined by physiological responses in that lactate doesn't rise above resting levels, and VO2 reaches a steady state within approximately 2 to 3 minutes. So you have the initial adjustment to exercise, and then VO2 is maintained at a relatively constant level during the exercise workout. Exercise can be maintained not without fatigue, but for an extended period of time, greater than 60 minutes typically. The demarcation of the moderate from heavy exercise intensity domains is the anaerobic threshold. And the anaerobic threshold is just an umbrella term for the lactate threshold, the gas exchange threshold, or the ventilator threshold. And it represents the transition from the aerobic reliance to additional supplementation with anaerobic energy supply. And so within the heavy domain, we have increases in the metabolic cost of exercise despite no change in workload over time. So even after that initial 3 or 4 minute adjustment to the exercise intensity, VO2 continues to rise slowly over time. And this is termed the VO2 slope component. Eventually, this VO2 will reach a steady state value. We also see increases in blood lactate concentration above the resting level, but those will also plateau and be maintained at an elevated steady state level. Within the severe domain, however, we see continuous increases in the metabolic cost in VO2 and blood lactate concentration until exhaustion. And exercise within the severe domain usually results in exhaustion within about 20 minutes or less. So the demarcation of the heavy from severe domain is theoretically critical power. And that is, critical power represents the highest power output that can be maintained without exhaustion for an extended period of time. So in this instance, at least 30 minutes, with steady state values of VO2 and blood lactate. There are also specific neuromuscular responses to each of these domains that are reflected in the electromyographic and mechanomyographic signals. I mean, specifically the amplitude and frequency domains of those signals. And this provides us information regarding the neuromuscular patterns of response during exercise. When we look at the responses in moderate exercise, we see typically no changes in motor activation strategies. Typically, amplitude and frequency remain relatively constant over time. When we look at these responses within the heavy domain, we may see gradual increases in activation and decreases in mean power frequency, suggesting that there may be some fatigue related to the action potential conduction velocity along the SAR dilemma. And then within the severe domain, we see greater responses in muscle activation and greater decreases in the mean power frequency, conduction velocity, and firing rate if we're looking at the frequency domain of the energy signal. So we conducted a series of studies to examine the validity of critical power relative to these exercise intensity domains. And this first study, we had subjects perform the incremental test to exhaustion to determine VO2 peak and GT, which we use to calculate the linear factor, and then they performed the 3-minute all-out test. So we were validating the protocol of Bonatello and Burnley. And then we had them ride to exhaustion at that critical power estimate. And what we found was subjects could maintain this intensity for only about 12 minutes, and there were continuous increases in VO2, heart rate, and the perception of effort throughout this workout. In a subsequent study, we followed the same protocol, determined critical power, and then we looked at times to exhaustion, the VE-VCO2 relationship, which theoretically below critical power should remain relatively constant over time, and above would result in increases reflective of hyperventilation or severe exercise intensity. And we also looked at the neuromuscular responses with the electromyographic signal. And we found time to exhaustion to be about 14 minutes with continuous increases in their VE-VCO2 relationship and increases in muscle activation over time, suggesting neuromuscular fatigue, and no change in mean power frequency, which can often reflect a balance between the effects of additional recruitment of fast twitch muscle fibers and the fatiguing effects where we see changes along the sarcolemma with action potential conduction velocity. So then we also looked at these responses during the same ride at critical power. We looked at the mechanomyographic signal. So mechanomyography is the measure of muscle sound, or the vibration of the muscle fibers. And the amplitude domain of this signal theoretically represents recruitment, where the frequency domain represents firing rate. And there are specific fatigue responses within this signal. So we looked at time to exhaustion, the metabolic changes, and the energy signal. Subjects maintained this workout for about 11 minutes, and we saw no change in the MMG amplitude or frequency, which actually, when we look at dynamic exercise and the MMG signal, that's consistent with previous cyclogrammetry studies at 80% of peak power, where often we see counteracting effects between recruitment, which tends to increase both of these domains of the signal, and the effects of muscle wisdom, which muscle wisdom is a theory that was proposed by Marsden in 1983 and suggests that during a fatiguing task, there's a decrease in the firing rate, an increase in the fusion of the twitch response, fusion of the twitches, and a decrease in the rate of relaxation time between firing. So this all results in an elongation of your twitch response and tends to lower the signal. So that can counteract any of the changes that we see from recruitment. So taken together, these studies suggest that critical power was not a sustainable intensity where VO2 and potentially blood lactate didn't reach steady state values and could not be maintained beyond 30 minutes, but instead resulted in times to exhaustion of 11 to 14 minutes and increases in VO2 and the perception of effort and heart rate and neuromuscular motor patterns that were reflective of fatigue with increase in activation. So the simultaneous examination of these fatigue thresholds allows us to make some hypotheses regarding the physiological mechanisms that may underlie these thresholds. For example, a gas exchange threshold, which is the demarcation of moderate and heavy exercise, is related to the change in hydrogen ion concentration thought to be the excess CO2 from bicarbonate buffering. We have shown consistently that the PWCFT that is reflected by changes in EMG amplitude is 10 to 20% greater than the gas exchange threshold. threshold. And taken together with our bicarbonate study suggests that hydrogen ion concentration may not be the most important factor affecting neuromuscular fatigue. We've also shown that critical power and the respiratory compensation point are representative of a similar exercise intensity and overestimate the demarcation of heavy and severe intensity exercise. The RCP is related to a number of factors, potentially the ventilatory response at the RCP. But recently there's some compelling evidence that increases in arterial potassium levels may affect that hyperventilation at the RCP. So it's possible that the level of interstitial potassium, potassium reaches a critical level within the muscle that affects the neuromuscular responses before it reaches a level in the arterial flow that affects the ventilatory responses at the RCP. So neuromuscular fatigue may be related to changes in potassium concentration. We also know that the decreases we see in mean power frequency within the EMG signal that reflect action potential conduction velocity are potentially related to the accumulation of ammonia ions, which are produced during anaerobic exercise and anaerobic metabolism. So these are all hypotheses that can be tested by measuring these metabolites and ions during exercise performed at these fatigue thresholds, and to further delve into what may be the underlying cause of the neuromuscular fatigue or the metabolic fatigue. One of the areas of interest to me is the application of the critical power model to physiological parameters. And recently, our lab applied this critical power model that relies on the relationship between the total amount of work and time to exhaustion to heart rate. So for this test, we plot the total number of heartbeats during a exhaustive workout versus time to exhaustion. And the slope of this line gives us a heart rate, critical heart rate, that theoretically represents the highest heart rate that we can maintain without exhaustion or for an extended period of time. So previously our lab looked at this model during cycloergometry, determined the critical heart rate, and then had subjects perform exercise at that critical heart rate and plus and minus 5 beats per minute of that heart rate. And to maintain heart rate, power output was reduced, which also resulted in a decrease in the metabolic cost of the activity and a decrease in muscle activation. So that tracked that decrease in power output. And there were increases in EMG mean power frequency and the perception of effort. So the neuromuscular responses were opposite of what we would typically see during a fatiguing exercise. And this occurred even though these same responses were observed at all three intensities, despite the fact that critical heart rate plus 5 was only maintained for 24 minutes and minus 5 for 52. The critical heart rate at 37 minutes was more sustainable than the critical power estimates that we had from the 3-minute all-out test. So it did represent a more sustainable exercise intensity. And the physiological responses were opposite of what we typically associate with fatigue during a constant power output test. So my work involved the application of this model to treadmill running. And we had subjects perform a VO2 peak test to determine the velocity at VO2 peak. And they then performed 4 constant velocity runs at a percentage of velocity of VO2 peak, ranging from about 80 to 105%, with times to exhaustion between 3 and 20 minutes. And we plotted the total number of heartbeats versus time to exhaustion, determined their critical heart rate, and then had them perform exercise at critical heart rate at 5 beats below that heart rate and 5 beats above their Each of these constant heart rate runs began at the velocity associated with that heart rate from the incremental test. And then we adjusted the velocity throughout the test to maintain heart rate. Most of the time we went down, but sometimes we had to bring subjects back up over time. And we measured the VO2, the EMG amplitude, and EMG mean power frequency, and the perception of effort responses throughout each of these runs. We showed that, one, the critical heart rate model was applicable to treadmill running due to the highly linear relationship between total number of heartbeats and time to exhaustion. And we also found that the critical heart rate represented a fairly sustainable exercise intensity, where -5, this actually represents every subject maintained the workout for 60 minutes, and we terminated exercise at 60 minutes. So this 56 represents the time to reach critical heart rate subtracted from the 60 minutes. So we didn't include in the time to exhaustion or the total time of exercise at the heart rate, the time that it took to actually reach that heart rate. And then +5, the subjects exhausted before 30 minutes. One subject was able to maintain the +5 value for an hour, but all others exhausted within about 20 to 25 minutes. And like psychogeometry, the velocity analogous to power output had to be reduced to maintain that heart rate. The metabolic cost of the exercise decreased, and the perception of effort increased throughout each of the runs. We also saw a decrease in EMG amplitude at critical heart rate -5, so that tracked the decrease in velocity, indicating a decrease in muscle activation, and an increase in mean power frequency. Increases in mean power frequency during a prolonged task may be also reflective of changes in muscle temperature. During a 60-minute run, the core temperature and muscle temperature is going to increase significantly, which tends to result in a increase in action potential conduction velocity, actually, so the sodium channels open more rapidly. We also see at critical heart rate, there was an increase in muscle activation in EMG amplitude, suggesting that additional fibers were recruited during the run to maintain this 48 minutes of exercise, and no change in frequency, reflective of potential balance between temperature effects and fatigue along the sarcal limb. And then at critical heart rate +5, for some subjects, the mean response was a decrease in amplitude, which may have been reflective of the fact that they started at a very high intensity and we took the intensity down rather quickly, and for some subjects they only maintained that critical heart rate +5 for 8 or 10 minutes. So the implications of these findings, if we look at exercise prescription, which is typically based on VO2 or heart rate parameters, there are specific intensity recommendations for the greatest improvement in cardiorespiratory fitness. And the ACSM's recommendations are that you perform exercise, vigorous exercise, which is defined as 64 to 90% of VO2 peak, for 30 to 60 minutes, 3 or 4 times a week. And this is often for people who don't have access to metabolic equipment. We prescribe this as a basis of percent of heart rate peak or heart rate reserve. So if we look at the percentage of heart rate peak, that's approximately 77 to 95% heart rate peak. When we look at the results of the critical heart rate studies where subjects perform exercise at a constant heart rate, we see the dissociation between VO2 and heart rate. So heart rate remains constant, but VO2 decreases, and within the study that I presented, that was a 9 to 14% decrease in the metabolic cost of the exercise throughout the workout. So if we're prescribing exercise just as a general, based on a general population percentage, if we suggest someone perform this exercise at 77% of heart rate peak, they're likely going to fall out of this metabolic range within that 30 minutes. So the majority of exercise wouldn't be performed within the metabolic range of vigorous intensity exercise. But interesting, what the critical heart rate study showed was that subjects performed critical heart rate and critical heart rate minus 5 beats per minute, which represented 91 and 88% of heart rate peak, respectively. They performed that for 30 to 60 minutes, and the VO2 remained within this range at 72 to 80% of VO2 peak throughout the workout. So for the sample population that I presented, critical heart rate minus 5 and critical heart rate provided a heart rate that was high enough to maintain the VO2 or metabolic cost within the desired range, but low enough to be maintained for at least 30 minutes, and may provide the necessary stimulus for the greatest improvement in cardiorespiratory fitness. So this is a potential training study where we can examine the effects of training at critical heart rate versus training at a general population percentage, and determine whether or not this actually does provide a greater stimulus. And this also leads us, all of these studies cumulatively leads us into several different areas. There's methodological studies, and there are a number of them, I'll just list a few, where we can look at variations in the critical heart rate protocol. So if we have them perform shorter times to exhaustion, and in our study we went to 20 minutes, but if we kept them between 1 and 10 minutes, how would that affect our estimates? Would we get greater estimates or lower estimates, and would those be more sustainable or less sustainable? And also looking at how the averaging that we use to determine the critical heart rate. So when we looked at those exhaustive constant velocity runs where we measured the total number of heartbeats, we took the heart rate from the initiation of exercise to the time exercise was stopped. So what would be the effect if we removed that initial cardiac adjustment to exercise intensity, the first 2 to 3 minutes of exercise? How would that affect our estimates? And then there's also some interesting studies regarding the PWCFT protocol. If you remember back to that initial slide where I showed you how the PWCFT is determined from a number of multiple submaximal work bouts and then averaged as the highest power output where there's no change in activation and the lowest power output where there is a change. For a 30-watt incremental protocol, there's a 15-watt potential for error. So between 230 and 200 watts, we estimated at 215. But that fatigue threshold could actually fall anywhere within those 30 watts. So to improve the accuracy, we can examine different workload increments and increments of maybe 5 or 10. But we also have to consider the practicality of that test and having subjects perform exercise for an extended period of time. And then there's mechanistic studies where we can measure the metabolites and ions during exercise at these fatigue thresholds and try to identify the underlying mechanisms. And then training studies, like I mentioned, with critical heart rate, looking at the trainability or the sensitivity of critical heart rate to training adaptations. If we measure critical heart rate before a training program and then after, do we see changes in our estimate of critical heart rate? Is it sensitive to training protocols? And we can also look at the application of these fatigue thresholds to different populations. And is it more sensitive to highly trained populations or recreational type athletes? Or are there clinical populations that may benefit from these type of testing? So there are a number of potential studies and questions that have arisen from the work that I've done previously. So with that, I will take any questions that you have. theoretically, it would be greater than the lactate threshold. So if we're looking, if you remember the
So
exercise.
define as maximum steady state lactate, that's what it would be above that.
If you define maximum lactate steady state is different from the lactate threshold. Yeah, so potentially it would be a similar intensity as the theoretical maximal lactate steady state.
How did you find the critical heart rate?
So do you understand the critical power model where we plot total work versus time? So we determine the total number of heartbeats during those same constant power output or velocity per unit treadmill runs. So we calculate the total number of beats, and that's analogous to total work. So those are plotted against time to exhaustion, and you get a very linear relationship. And theoretically, the slope of that line, that's a heart rate, which theoretically represents the maximal sustainable heart rate. And the key to that concept is it's the maximal heart rate or the maximal power output, not just a power output. So you're identifying that demarcation ideally, but a lot of work has shown that it overestimates. And so the application of the physiological mechanism was to try to improve that estimate. Yes?
So you mentioned the ACSM guidelines. Would you propose a revision of those guidelines just to incorporate some of the variables that you presented, or do you think that the guidelines are satisfactory as is?
Potentially, I think we need more studies to determine if this is actually a more effective training program before we make any revisions. But I think if you look in the ACSM guidelines, it's all based on all of the variables that they present: VO2, heart rate, RP, perception. Those are the three main ways that they recommend exercise prescription. And all of the relationships that they talk about are based on incremental or constant power output exercise. And the responses, the physiological responses that we see, differ depending on how you maintain exercise. So if you actually maintain heart rate, you don't get the same physiological responses that they base those relationships on. And I think it's going to take a lot of time for people to make any type of adjustments or guideline recommendations. We need studies to look at that. But right now, at the University of Lincoln, one of my fellow graduate students is looking at exercise based on perception of effort. So when we prescribe exercise based on RPE, the responses are very different as well. So I think it's a process of doing more studies and finding out how best to prescribe exercise before we can make set recommendations. Yes?
So do you, by what you know about critical heart rate, do you think it would be a better way to train, basically then train, or?
The really nice thing about critical power or critical heart rate is that it's an individualized threshold. So it's not based on a population recommendation, it's based on an individual's capabilities. When we recommend VO2 as, say, 60 to 80%, that can be a very different intensity for me than it would be for you. If 60% is my lactate threshold, but that's way below yours, those exercise responses are going to be very different. So that the key to the critical power concept and the application of these physiological parameters is that it's an individualized exercise prescription rather than a population. And potentially, and that's where we need studies, is to compare to see if this individualized training basis does result in greater adaptations. And there's actually also potential for people who run a lot, anybody who runs a lot or swims a lot or does one specific activity and trains relatively intensely at that, you know how fast you can run, and you can probably identify your critical velocity or your critical swimming velocity just based on your own knowledge. So you can, say with a swimming team or a track team, you can ask them how long they think or how quickly they can run a set distance. So like in track, how fast can you run 200, 400, 600, 800? You have 4 workouts right there, and you can estimate their critical velocity for them. So we might not even need to do the multiple workouts if you have a highly trained population. But the validity of that hasn't been examined, so that's another potential area.
So the studies, the majority of the studies are in a population that are younger, healthier populations. That's where the data is coming from.
Yeah, these are all from college age, recreationally trained populations. I didn't do any studies with highly trained athletes, and all of my subjects were between 19 and 29.
So the implications that, like Dr. Flanner was talking about, when you get into older populations and looking at people with different disabilities, whatever their illness, disease, event, critical heart rate would be something that would be a better indicator for them, or in terms of prescription.
Potentially, I mean, you have to consider the ability of elderly populations to perform maximal exercise. So it may be limiting in that we can't do these protocols with elderly or obese populations because they just can't reach those maximal intensities. But there are a number of other fatigue thresholds determined from submaximal protocols for prescribing exercise. And actually, the PWCFT concept, heart rate and VO2 have both been applied to that concept. So there is a PWC HRT, which is theoretically the maximum heart rate you can maintain for an 8-hour workday. And that's been used a lot in factory working settings where people are working on an assembly line or loading a truck and repeating muscle actions. So what is the highest heart rate they can maintain throughout the day without getting fatigued and having to quit? So there are those potential applications.